JQI seminar. So we're doing something, not quite our usual today. So we're going to actually have two talks from two of our own postdocs. And so please don't tune out when the first talk ends. There is a second one. It's going to be good. So other than that, we're running on our usual format. So we have some people on Zoom and some people in person. If you're on Zoom, please keep yourself muted until you have a question, in which case feel free to interject. And please tell the speakers your name when you ask the question, because we really can't read the small name in the corner. And so, as I said, we'll be having two talks, one experimental and one theoretical talk. And so our first talk will be given by Farfurnik, who is a postdoc in the group of Ido Walks. And he's going to be telling us about all the fun things that they're doing. So, Dima, take it away.
All right. That's awesome. Okay, let's try this. Does this work? All right. Let's see if this works. Okay, good. So thank you very much for the introduction, and thank the committee for choosing me to give this talk. I'm going to talk about coherent control of optically active solid spins for quantum photonic applications. Single photons are very useful resources for quantum applications. For example, they can be used to perform quantum computing and simulations of interesting physical problems, and they can also form a way to communicate between separate quantum nodes for the formation of the future of the quantum internet or quantum networks. In this sense, one resource that is very important for these applications is to use systems that have both spin and optical properties. Such systems can emit single photons in a deterministic way, and also such systems could feature spin that could contribute to the generation of photon-photon interactions. So far, linear quantum computing is limited because photons do not usually interact with each other, but this can be enabled by spin systems that have also photonic properties. For example, in our group, in the Ido Wax lab, we've been studying for some years these quantum dots. These are optically active systems of one wide bandgap semiconductor that is embedded in a narrow bandgap semiconductor that is embedded in the wider bandgap semiconductor. The difference between the lattice constant of these materials introduces strain that produces these quantum dots. And if we deterministically charge our samples using voltage bias, these quantum dots can be charged with electrons, which under the application of external magnetic field form this very useful energy level diagram that consists of electron ground state spin and excited trion states. Now, these quantum dots are mostly useful because these excited state emits single photons with great brightness and great indistinguishability, which makes them a very promising system for these applications. And also, if we want to introduce photon-photon interactions, we can leverage the spin of these electrically charged quantum dots, like has been done in Ido's group several years ago, where the spin of the quantum dot can be strongly coupled to a cavity, and effectively lead to these photon switching and these photon-photon interactions. But this is just one example of such system. There are many more examples of useful systems that are based on quantum dots, quantum dot molecules, etc. And these are the systems that we are interested in studying. One main challenge in studying these systems and utilizing them for quantum photonic applications is that we need to be able to leverage the spin. Namely, we need to be able to arbitrarily control and read out the spin state, and we also need to deal with noise sources that cause spin decoherence and try to optimize the coherence time. So first, I want to address how to Yes.
This is Bill Phillips.
Yes.
Could you just say a few words about why it is that putting a narrow band gap embedded into a wide band gap gives you the kind of properties that you want?
So basically, what happens is that you have an electron confined in the system, and oops, sorry, I did something wrong. You have an electron confined in the system, and then you can shine light. And when you shine light, you create another electron and hole pair, and this electron and hole pair has this photon emission properties. Now, this whole structure that allows you to capture this electron in the first place is formed due to the mismatch in the lattice constant between the materials. This mismatch between lattice constants leads to some particular points of strain. And this strain is what allows us to capture these electrons and have these properties. Basically, this is the confined quantum system that you see here. This it's system that is confined mainly in this direction. You have something like 5 nanometers in this SEM image, and this is something like 20 nanometers, and this is what produces these photonic properties. I hope this answers the question.
Well, I'm still not seeing the point about the narrow band gap and the wide band gap.
I think if the host.
But maybe we should just go on.
Yeah, why don't we talk after?
Yeah, maybe we can discuss that. Like, yeah, I mean, the narrow band gap and the wide band gap is what forms you the potential well that captures the electron, right? So is that what you mean?
I think the key is that you can have states in the narrow band gap that aren't allowed to spread because they're in the band gap of the host.
Yes. So this is the potential well that captures them. Okay. Okay. Sure. Okay. I guess I didn't get what. Yeah. I'm sorry about that. Okay. Anyway, so the way to control this, usually the way to control spin qubits is simply by driving coherently, driving the system with the field with this energy level difference, and it's usually done in diamond, silicon carbide, and other materials by using microwave fields. But in some systems, this approach of microwave field is challenging. For example, in these quantum dots, we need to use resonance frequencies of several tens of gigahertz sometimes, and the G factor of this electron spin is sometimes like something like 0.4. So it's very challenging, and if it's challenging, it doesn't mean that we don't need to address this problem. So together with Alessandro Rostelli here in JQI, we're trying to develop a novel fabricated microwave delivery system using these PCBs with these nice terps on top of them, and a coplanar waveguide to deliver this high frequency microwave fields. But still, this work is preliminary. So typically people, and we as well, use all optical approaches for the coherent control of our spin system. And basically the idea is that instead of directly driving between the 0 and 1 state, we introduce optical fields, 2 optical fields that have a common a state that is detuned from our excited state, and by driving simultaneously these 2 optical fields, we are able to transfer population from 0 to one and vice versa, and generate any spin state that we want. This has been introduced in the quantum dot community only 2 years ago here in Cambridge, where they performed such spin control to perform Rabi oscillations. Now, previously, this technique used ultra-fast lasers, but with the ultra-fast lasers, you can actually apply pulses with arbitrary phases and times as you need to control the quantum state of these spins for arbitrary applications. And the ability to achieve this two-photon driving is enabled by taking a CW laser, injecting it through an electro-optical modulator, and this electro-optical modulator creates two sidebands whose frequency difference matches this energy gap, and effectively performs this spin rotations. And if you use an arbitrary waveform generator to perform this modulation, then you are able to create pulses of arbitrary spin control of these states. So once we are able to control the states, what we're interested in is to be able to provide qubits with long coherence times. And we need, for that, we need to be able to characterize the noise sources in our systems and try to overcome them to prolong the spin coherence times. So this is what I want to talk about right now, how to characterize the noise sources that lead to decoherence and decouple from them. So this is something that has been using techniques inspired by NMR several decades ago, and I think the first idea to use it for the extension of spin coherence time and for noise spectroscopy was introduced in 2008 here, by the Sarma group. And the idea is that we have a noise spectrum of our spin qubit that causes decoherence, this S omega, and we would like to extract the frequencies of these noise, the power spectrum, and the strength of coupling of different frequencies to the spin, which is essentially causes decoherence. So the way to do it is to apply a pulse train, a pulse sequence that controls the spin state, like I said. After this application of this pulse sequence, both the noise source and the pulse sequence affect the spin dynamics. So we measure the spin dynamics and as a function of the spin interrogation time in the experiment. So this has been performed in many spin qubits, superconducting qubits, spins in diamond, silicon carbide, etc. Here is one example for this use of pulse sequences introduced in the Ron Walsworth group at Harvard for NV centers in diamond, where they also performed this kind of noise spectroscopy. And the last stage of this noise spectroscopy is that there is a formula that connects between this function phi, which is essentially the logarithm of the spin dynamics that you measure, S, which is the noise spectrum that we want to extract, and F is the known temporal domain filter function of the pulse sequence that we applied. So here, for example, in NV centers, they used this numerical deconvolution integral to extract the noise spectrum of spins that interact with NV centers. And here, what we do, we establish this all optical approach to control the optically active spins. So we want to use similar sequences to study the noise spectra and also know how to mitigate them on the system of quantum dots. So, okay. Yes. So when we do it, we study the noise spectra of quantum dots under application of these pulse sequences. These pulse sequences are called like the CPMG pulse sequences. They were introduced in NMR many decades ago. And the idea is that you apply many pi pulses, and if the rate of application of these pi pulses is faster than the frequencies of the noise, you are able to decouple from the noise. If they're slower than the noise, you actually can recouple noise or make it stronger. So when we apply this CPMG pulse sequences on our system, we study their effect on the spin dynamics on quantum dots for different external magnetic fields and different numbers of pulses. So for example, if we use here a field of something like 1.2 Tesla, we see that when we increase the number of pulses, the coherence time grows, which means we were able to decouple from noise. But on the other hand, if we increase the magnetic field, we see that if we also increase the numbers of pulses, the coherence time doesn't increase again. And this is because probably the noise spectrum is very different. So we actually know from theoretical modeling what are the noise sources of these quantum dots. Basically, the quantum dot interacts with tens of thousands of nuclear spins in the environment that are also broadened by the strain field that produces the quantum dots in the first place. And by this theoretical modeling, we're able to reproduce the experimental results from the theoretical model. But to really understand the whole picture on the power spectrum of these noise sources and be able to decouple them, we actually need to perform this the convolution integral to extract the noise spectra. And when we do it, this is what we get. This is the noise spectra of these quantum dots that we measured for different magnetic fields. The blue curves are the experimental extraction from our spin dynamics, and the red curves is simulations. And while we're still unable to perform high resolution spectroscopy to resolve the tiny features of the simulations, we do see that the profile of this noise that we measure is similar to the simulation, and we know how to explain it. Basically, this noise consists of two components. One component is the main features that you see here. They're related to the Larmor frequencies of the nuclear species that are broadened by strain, and another feature is here looks like constant background, but it's not constant, it's monotonically decreasing, and this also something that relates to the same hyperfine interaction, but in the perpendicular direction to the field. So by looking at that, we know that when you increase the magnetic field, on the one hand, the frequencies of the noise increase, which makes sense because when you increase the magnetic field, the Larmor frequencies of the nuclei increase. But also we see that when you increase the magnetic field, the magnitude of the noise decreases. And this is also makes sense because the inhomogeneous broadening of these nuclei become relatively small to the axial field, the axial Zeeman field that forms their main energy. So we understand how this works. And while we were unable to apply many pulses to extend the spin coherence terms of quantum dots beyond the state of the art, which is a microsecond, continuing with the simulations shows that if we are able to apply hundreds of pulses of pi pulses, then we'll be able to extend the quantum dot coherence time beyond 10 microseconds. So the problem, yeah, sorry.
This is Bill Phillips again.
Yes,
I'm not understanding the thing about the homogeneous broadening. This is a single quantum dot, right?
Yes, it's single quantum dot, but it interacts with tens of thousands of nuclear spins. These nuclear spins have some coupling to the quantum dots, but they also they are placed in a strained environment, in the sense that different locations of these nuclear spins, they are like broadened by this, they interact with the strain field. So the way it works that if you just consider the natural Hamiltonian of these nuclear spins, you have just their Larmor frequency times Bz. But because of this unhomogeneous strain, they have another component in the Hamiltonian, which is some quadrupolic coupling. And this quadrupolic coupling changes the eigenstates of the system, which makes things like more complicated and which results in these noise spectra that you can see.
Okay, but what I'm not understanding is it seems that if everything is static, then the inhomogeneity of the nuclear fields isn't going to bother your single spin. Is this a time inhomogeneity that
Yes.
you're talking about?
So if you look at the Hamiltonian of basically the way we calculate the spectra, we say that we have many nuclear spins, that they form some effective field that interact with the quantum dots.
Sure.
This effective field is time varying. Now the
Okay.
question is how we calculate this time varying effective field, and in order to do that, we need to use the full Hamiltonian of the nuclei, which has two components. One component that shouldn't lead to these noisy features, and this is just the regular Zeeman field, Zeeman term of the nuclear spins. But another component has some quadrupolic coupling due to the strain, and this actually changes the eigenbasis of the nuclear spins, and with this and this creates this time varying field that interacts with the dot and looks like these red curves.
So what temperature are these experiments done at?
4 Kelvin.
Would this get better if you were at 10 millikelvin?
So I don't think it will get better. I think that what will get better is all the effects that are related to phononic interactions, like phonon-assisted spin orbit coupling and stuff like that. But these effects they're not assisted by phonons.
Well, what is causing the time variation? That's what I'm missing here.
What is causing the time variation?
Yeah, the thing that's bothering you, if it's not phonons, what causes these nuclear spins to as you know, the strain, what causes it to change in time?
So
have a bunch of slightly different Larmor frequencies.
yes, you have slightly you have slightly different Larmor frequencies and eigenvectors because of this additional environment of the strain.
Okay, I see what you're saying. That it's like all the spins are beating against each other as they precess.
Yeah, maybe you can consider it. Yeah.
Okay.
So we can. Yeah, I have this the full expressions of the Hamiltonian. We can look at them, but basically there are terms that are proportional to the nuclear spin operators that multiply each other, like quadratic terms of the nuclear spin operators. So I don't know if this specifically answers your question, but basically, if you just straightforward diagonalize the Hamiltonian for each spin separately, you see that there is like temporal dynamics because like different spins create different fields and different random frequencies. Yeah. So we were unable to apply those hundreds of pulses. How am I with time? Between 5 and 10 minutes. Great. So we wanted to apply hundreds of pulses to decouple from these noise sources and be able to extend the coherence times. But we encountered one major problem, is that when we applied more and more pulses, the contrast, meaning that the fluorescence contrast that we measured dropped more and more with the number of pulses until we were unable to measure anything after application of more than 8 pulses. So as opposed to the other system where this kind of drop of contrast is associated to pulse imperfections, in our case, it is a different cause. Basically, what happens if we apply more and more pulses, we introduce stronger and stronger laser power because each rotation pulse brings more and more rotation with the laser, and when we add this laser power again and again, what happens is the electron that is confined in the quantum dots just tunnels out of our sample, starts tunneling out of our sample, and we can measure this rate of tunneling as a function of the laser power, even if our laser is not modulated at all, meaning that should not perform any rotations. So this is a laser that introduces spin rotations, and this is laser that is not modulated, that shouldn't introduce any spin rotation. So we see that basically the contrast of the Rabi oscillation that we see with this rotation is limited, because just when we shine the laser light again and again, the electron of the quantum dot disappears. And as we can see also from these Rabi oscillations, we're able to apply something like 8 pulses. And the direction that we want to solve this issue is that we want to use quantum dots that are interact with photonic structures. So inspired by this previous work by Kartik, we also embedded these quantum dots. We fabricated them. We fabricated these circular gratings, so-called bullseye antennas, on our samples. And the idea was that if we have a quantum dot that interacts with this bullseye antenna, then these antennas have 2 advantages. One advantage is that they're pretty directional, in the sense that their far field emission for both polarizations look simply like a Gaussian function, and perfectly fit the NA of our measurement, which means that if we want to control the quantum dot and perform spin rotation, then we will be able to apply much lower laser powers to rotate the spin. If we apply lower laser powers, then we will be able to perform much more spin rotations for these applications of dynamical decoupling. And another advantage of these bullseye antennas, that they also introduce the so-called per cell enhancement of this emission of the excited states of the dots. So what we can see here is that this preliminary work that we did shows that these bullseye antennas give us quantum dots that was optically excited states, emit photons at sub 100 picosecond lifetimes, which is comparable to the highest lifetimes, the best lifetimes measured with the above band laser in micropillars. And this is a per cell enhancement of 15 over bulk dots. And we also see that this kind of behavior, we can also locate charged dots on top of these bullseye antennas and perform optical pumping of such dots. And the collection efficiency that we measure for addressing these dots, so far, it has been 25 times larger than dots in the bulk. So this is why we hope to be able to use these structures to boost the capability of spin rotations by introducing lower laser powers and enable all these applications. So one other thing that I want to mention, that if we enable this application of pulse sequences of hundreds of pulses, we're not only able to increase coherence, the coherence time of spins, but we should also open new avenues for many quantum applications. First of all, we should be able to generate controllable spin photon entanglement and be able to control the spin state arbitrarily using pulse sequences within this region. And also we should be able to preserve arbitrary quantum states of spins. We should be able to apply novel sequences for high resolution sensing. They require many pulses. And this is also interesting work that we are working on, led by Kai-Xin Huang, together with Muhammad Hafezi and Yikai Liu. The idea is that you can use random systems of random pulses to not only measure power spectrums of noise, but also to measure some useful functionals. these nodes. So to conclude, I showed you some directions to optically control optical active spin systems, and how we perform noise spectroscopy to measure their spin dynamics and get some insights on dynamical decoupling. And we hope to enable the application of multi-pulse sequences for all these quantum photonic applications, from boosting the spin states of these systems. One thing I want to mention, as this was done mainly on indium arsenide quantum dots and gallium arsenide, and those dots have disadvantages. One disadvantage in the optical emission properties, and is that, okay, they emit at something like 950 nanometers, and it would be great if we could use we could study other optically active spin systems that emit at telecom wavelengths, because telecom wavelength is extremely efficient of communication, and also the spin properties of these quantum dots are still relatively short. So like we could again use the dynamical decoupling to extend this, but we also can use other systems. There are some efforts today to grow and utilize dots by other techniques like droplet epitaxy that don't have this strain and don't have this all these time varying components of noise. Another approach is to take two molecules and stack them on top of each other. This system forms a decoherence-free subspace of prolonged coherence time. So basically, we introduced a set of techniques that could enable the studies and development of novel spin systems. So I would like to thank the committee again for choosing me to give this talk. Ido Wax, of course, my host here at UMD, my colleagues Harjot, Jochen, and Robert, and the team at the Naval Research Laboratory that grows the samples and provides us with lots of insight and useful discussions. And I would like to thank my funding sources, and also thank you all for listening.
Time for a couple quick questions.
So I have another question, but if there are others, you should take those first.
One from the room, Bill. So let's take that one first.
Wait, so in the last part, what do you exactly mean by spin photon entanglement? Are you generating entangled photons from the dot, or you want to actually entangle one photon with the spin of the dot that you have?
So I can say both. So these dots can be used to generate photons, but here by spin photon entanglement, I meant that that you can let me use this cool option too. So if you incorporate these spins and cavities, basically, if you have strong coupling on you have strong coupling between the spin of and the cavity, then basically you can entangle between this the spin and the cavity, in the sense that for example, if you shine a photon and you look at the polarization set of the photon, then the photon is reflected with one polarization whether the spin was up, and with another polarization whether the spin was down. So here you can, for example, create this Bell state between the spin and the photon, and what the cool thing that we want to do is to be able to coherently manipulate the spins with the rotation pulses. This process. So to measure this entanglement, so the question is how you define to measure this entanglement, and people usually look at some okay, it depends on whether you are able to measure the entanglement or no. It depends on the fidelity of your spin preparation and rotation. So this is what we want to pursue next, because here in this demonstration, the fidelity was not high enough, but we want to push it with the because we want to be able to push it, because we use quantum dots as samples that are deterministically charged, and two, we apply these rotations with modulated laser rather than ultra short pulse laser. And these seem like technical advantages, but these technical advantages should enhance the fidelity of spin readout and in preparation for arbitrary states, which will allow to measure this entanglement.
Okay, so Bill, we probably have to just move on to the next speaker.
Sure, no problem.
Yes.
If you guys can try to do that, switch slides.
Thank you.
So our next speaker is Mathias van Regemortel.
That's correct, yeah.
Close? Okay, excellent. He's a postdoc with Mohammed Hussein.
Thank you. So today I will tell you something about how monitoring dissipative dynamics or open system quantum dynamics can induce transition for their entanglement entropy, and also how it affects the sampling complexity of the jump outcomes. So for this, I basically want to draw a connection between three different things. So first of all, so what do we mean with this monitoring of the quantum jump? So first of all, we have an open quantum system, so we have some dissipative dynamics. And these dissipative dynamics can either be described by a master equation or by a stochastic trajectory, so in this unraveling picture of the master equation. And now I will explain what I mean exactly with this unraveling. And this unraveling is not unique. That's something that we will emphasize here. And on the other hand, we also have this monitoring or measurement-induced phase transition, which is usually studied in circuit models. And so there, the idea is that you have some unitary gates which entangle a chain of, so you have some register of qubits, and then they're alternated with projective measurements at some probability, with some probability p, and then depending on this probability p, there is some critical value where you go from volume law to area law scaling for the averaged entanglement entropy. And then last, we also have boson sampling. So that's a sampling complexity if you have single photons which are injected in some linear optics interferometers, and then sampling the outcome probabilities is sharply hard, and therefore it has been a proposal for quantum advantage, and there have been some recent experiments. And so now we want to draw a connection between these quantum emitters and these quantum jumps and boson sampling. So this brings me to my overview. So first of all, I will explain exactly what I mean with this unraveling of master equation and how it relates to monitoring dissipative quantum jumps. And second, I will draw the connection with measurement-induced phase transition in the sense of a monitoring-induced phase transition here, and how it affects the scaling of entanglement entropy if you have two competing monitoring protocols. Then in the third part, I will draw the connection between this boson sampling and the way you monitor your jumps in a dissipative quantum system. And four, and that will be more the outlook, I will make the last, or at least present some ideas for the last connection, where we have an entanglement scaling transition, which is directly related to the sampling complexity of your jump outcomes. So first of all, what do I mean with quantum jumps? So let's start very simple. So you have some dissipative systems, so driven spin, which also dissipates, so it can decay. And now when it decays, it emits a photon, it spontaneously emits a photon, and we assume that we can collect or record this photon as a jump click, and that we can therefore record or reconstruct its trajectory. So for example, here we have some coherent oscillations from, wrong button. Yeah, so we have some coherent oscillations from the Hamiltonian, which is just drive, and then at random moments which we have to sample, we see the jumps and we go back to the ground state. And if we do this again, we will sample a different trajectory with jumps at different times. And if we sample many trajectories and we average over all these trajectories, we converge back to the results from the master equation. This is something that is important.
Could you say why, this is Bill Phillips, could you say why some of these jumps take you down to zero, which is what I would have expected, but some of the jumps don't seem to take you down to zero?
Oh no, they should. They all take you down to zero. It's just that's numerical inconsistency. Okay. Just the sampling rate of my numerical points. Yeah, sorry, that's sloppiness from my side. Okay, so these converge back to the master equation if you take many trajectories. So more formally, what do we mean now with monitoring these quantum jumps? So if we have a state, pure state psi at some time t, and we want to know the probability of having a jump ci, which is some operator, we have to evaluate this expectation value. Here's my pointer. Yeah. Anyway, so it's the C dagger ICI, and then this expectation value, and then multiplied with time interval delta t and some gamma, and then the total jump probability is the sum over all these probabilities. And then we have two scenarios. So either we see a jump, we apply the jump, we get a new state, or two, we have no jump, so 1 minus delta p, and then we have to evolve with a non-Hermitian Hamiltonian, because basically we get some information from not seeing a jump as well. And then in general, these two, they do not conserve the norm of your quantum states. We have to normalize again, we get the new states, and we can repeat the process. And this way we can sample the trajectories. There's something wrong there.
I have a question while that's happening.
Sure, yeah, go.
So since there's multiple unravelings of the master equation, how do you know, this is almost like philosophy, but how do you know which one will correspond to physical reality?
Well, I will actually get to that, and also how an unraveling corresponds to your monitoring scheme, which is one of the things I want to explain now. Yeah, so I will get back to your question.
First order debugging failed. We have no laser pointer.
Okay, now then I try to speak more clearly. And anyway, so we can sample these trajectories now and sample the random jumps. And then we know if we have some register of, or a record of all the jumps that we've seen during the time evolution, at which time we see which jump, we can always reconstruct the pure state dynamics of our dissipative system. And we don't have to resort to the master equation, which generally leads to a mixed state. And so first, the first connection is this with the monitoring induced phase transition. And this is work that has been published last year with some people from Mohamed Hafezi's group. So with Sepai, Ali Reza, and Hossein, and Mohamed, of course. And so here the idea is if you now have two monitoring protocols, so we have two people that monitoring dissipative processes of your system, but they don't quite agree with each other, and there is some conflict between them. And now we want to study how this affects the scaling of entanglement entropy of your system. And so, what is the model exactly that we're looking into? So we have a cavity chain, so bosonic modes, a chain of bosonic modes, and two interacting number conserving monitoring protocols. There is no system Hamiltonian, so everything is just dissipative. The first monitoring is just local dephasing, so we do a weak local measurement of particle number. Second, we have phase locking, we call it. So in this jump operator, the blue one there, has been presented in 2008. And it has been shown that it stabilizes a BEC state, so Bose-Einstein condensate state. So it basically condenses all particles in the zero momentum mode, and therefore it generates long-range entanglement throughout the chain. And so now we know that these D operators, they generate entanglements while C destroys it, and then can think of it as some kind of dissipative hopping versus interaction. And now the central question that we have is, how does this affect the stochastic pure state dynamics of our psi T of our trajectories? And we will study everything in terms of this small gamma, so that's the ratio between the dephasing rate and the phase locking rate. So first of all, what do we mean with the monitoring exactly? And here I show, so these are two cavities, these AJ and AJ plus 1, and they're now coupled above to an ancilla qubit together. And then the idea is to implement some effective Hamiltonian, this G effective TJ sigma plus, where sigma plus is the ancilla, and that this ancilla is very dissipative. So immediately when it gets excited, it decays again, it emits a photon, and we can collect this photon, we can register it, and therefore we can record the jump. And so the same for dephasing. And if we just do a simple simulation of these two sides, we see that in general, blue jumps are phase locking, so they generate entanglement. So entanglement goes up while the red jumps are dephasing, and then the entanglement goes down. The same if you look at the occupation of an ancilla level, it's pretty much zero just because it's very dissipative. And now we want to study the trajectory entanglement entropy. And what do we mean exactly with that? So first, we have these stochastic states in a chain of length L, and we have this control parameter gamma. And now we have a subsystem A consisting of small L sides, and we can compute the reduced density matrix of the subsystem. From there, we can obtain the entanglement entropy of this stochastic state of subsystem with size L. And from there, we can average over different trajectories, and we can get to an average trajectory entanglement entropy, which is given there. So we sample NT trajectories, and we get an average entanglement entropy. And so now single trajectory, we expect, like the lower right plot, that it shows some fluctuations depending on the jumps that we see. And now we want to look at in the long time limit where we expect to reach some stable regime. And if you look at entanglement entropy scaling with subsystem size in this steady state, in stable regime, we see that if we have a large gamma, so large dephasing, that aligns or flat in the bulk roughly. So we basically see an area law depending, so no subsystem size depending in the bulk, no subsystem size dependence in the bulk. But then if we go to lower gamma, we see that we start to see some curvature in these curves for entanglement entropy. And so the same with system size here. So the red line, so large gamma is roughly flat. So no system size dependence, but then the black line shows like some dependence on system size. And then with the, here now the axis is gamma. So we see there is some critical point where the lines of different system size start to deviate from one another. And then we can, or we know, at least if gamma is 0, that we must have some a critical scaling, so logarithmic scaling of entanglement entropy with some effective, or with some central charge. But now, as of the dephasing, we can get an effective central charge, the C gamma, which is also given in the first figure there from the lines which we just obtained from a fit. And from this, if we plot this for different gamma, we see that there is some transition point, or it's difficult to say exactly because we limit it to small system sizes. But then if you look at different Renyi entropies alpha, we see that they all give the same central charge. So there is a formula for this for conformal field theory, where you can find the central charge from different Renyi entropies. And they also show some power law divergence if gamma goes to 0. And so this is a signature of transition from critical to area law scaling for entanglement entropy. And then, so we have this transition, and we assume there is some critical gamma where you go from area law to critical scaling. And this is kind of reminiscent of what they see, this measurement-induced circuit models. So this measurement-induced phase transition in circuit models, where, so on the right plots, you also see this transition depending on the critical measurement probability, where you either go from an area law to a volume law in their case. And there have been studies for other monitoring-induced transition too, in particular in this work, where they look at free fermions, which are also subject to dephasing, and there they see a similar transition for the entanglement entropies, and they could go to larger system sizes. So this brings me to the next part here. So the correspondence between these jump statistics and Fock state boson sampling. And this is something that was done in collaboration with Ole Stanko and other people from both Mohamed Hafezi's group and Alexei Korshkov group, Luis Pedro, Abhinav, and Hossein. And so here the idea is, so someone monitors your system, but is not quite sure as to how to monitor it. And now the question is, how does choosing a different monitoring scheme for the same distributive process affects your jump statistics, or the sampling hardness of your jump statistics, and also the trajectory entanglement entropy, and how are they related to each other? And so first of all, what do I mean with the invariance property of a master equation? So we keep the master equation invariant because we keep the same dissipation. The only thing that we change is the monitoring. And so the first thing that we can always do is we can do some unitary rotation of the jumps. And this physically corresponds to monitoring your spontaneously emitted photons through some linear optics network. And you can just easily check if you plug this into the master equation, you see that you get the same master equation again, so it's invariant. Same if you add a classical field, and this is a homodyne detection scheme, and this also gives you the same master equation invariant. So that's invariant. And we will focus in particular on the first, so the unitary transform. But so what does that mean, master equation invariant? So that means that any expectation value is the same. So regardless of fourth choice for C, for the jump operators, it's always going to give the same expectation value of observables. However, these trajectory states, these stochastic states, they are jump dependent now, because if you apply a jump on a state, it will be different depending on which unraveling the which choose. However, linear properties, after averaging out, they should converge again to the master equation, so this should always be the same, but nonlinear properties not. And one such nonlinear property is the entanglement entropy, same as what we were studying before. And so a very simple example of what we mean with changing the jump, of changing the monitoring is we can see this with only two spins. So there is no Hamiltonian. We just start from two spins that are excited, and they dissipate with some rate, say uniform rate. And now we do a direct monitoring of these decays. So we have two jump operators, with C1, which is just the decay of the first spin, and C2 is the decay of the second spin, and the unitary is just identity matrix. So we can have now two scenarios. So if we detect a jump click, it can be either in the first detector or second detector. So we have either the first spin that's decayed or the second spin that decay, something that we know, and then we will see another jump and we will get to the vacuum state where all spins are down. So not very surprising, you always detect clicks, one in one detector and one in the others. Click sequence 1, 1. However, if we now do the monitoring through a beam splitter, a 50-50 beam splitter, or unitary is now maximally mixing, and we get two new jumps which are maximally mixing. And if we have a symmetric jump, which is C1, and the unsymmetric jump, which is C2. And now if we start from all spins up, we detect a click, say we detect C1, we will generate some maximally entangled symmetric Bell state. If you see C2, we get an antisymmetric Bell state, and then this one can only decay with the same jump again. And so this is the same as what in photonics is known as Hongel-Mandel effect, where with a probability of 1/2, we either detect jumps 2, 0, so 2 in the first detector, 0 in the second, or 0, 2, so 0 in the first detector and 2 in the second. And so now we can generalize this and have more spins. So we have n spins now and some interferometers. And this gives us new jump operators, which are given here. So there's just some unitary rotation of sigma minus j. And for this part, we will focus on u being some random unitary, so some random unitary that has an overlap with all spins. And now all spins start from being up, and then the clicks are monitored through this u, through the linear interferometers. And now the spins, in principle, they decay sequentially, or at least each click is sampled independently from a Poisson process. And now if we register a click, this will give a buildup of entanglement entropy, of entanglement between the spins in the chain. And so here is a plot of that. So the red lines are different trajectories. And so this is a system of 18 spins. So we see we start, of course, with 0 entanglement because all spins are up. And after detecting 18 clicks, we know all spins must be down. But then we see that entanglement grows, it reaches some maximum, and then it goes down. And then we can compute the average of all these trajectories, and that's the thick blue line. And now if we plot this maximal entanglement entropy for different system sizes, we see that it goes straight up, so it clearly shows volume law. And this can be understood better if we just look at the different curves for different system sizes. And then we see indeed that that the maximal always goes linearly up, even though the start rate is the same for all system sizes. And then a little bit more general, if you now have, or how does this affect the jump statistics? And for this, we make it a little bit more general. So we have n spins and n input arms of the unitary. And so we have m spins excited in the n input arms, the jump. And now we can show that these jump outcome statistics are exactly the same as what you would get for boson sampling. And for this, we need to evaluate the probability of detecting n1 clicks in the first arm, n2 in the second arm, and so on. And this is given by this expectation value. And if you just plug in the right expression for the CI, and it's like 2 lines of calculation, you see that you exactly get permanent again. And this permanent is known as like or at least the proportionality of your probabilities to this permanent squared is known from boson sampling, where you have n single photons or indistinguishable single photons that are incident in a linear network, and then you sample the outcomes. And so this UT here is a submatrix of U, which corresponds exactly to the click outcome or the photon outcome that you want to evaluate. And this sampling is believed to be sharply hard on a classical device, and this has like some implications for complexity theory and everything. However, this is maybe not so surprising because the spin is just a single photon emitter, so in the case it emits a photon. However, what is kind of surprising, at least to me, is that now we have this sequential decay, so each spin decays independently, and this comes at the cost of generating entanglement between your spins. Whereas for photonic boson sampling, you need to have that all your photons are indistinguishable, and therefore they have to be incident in your interferometers simultaneously to ensure the many body interference. And now we can look how the entanglement entropy now depends on the network configuration that we use for monitoring. Oh yeah, but this is the last slide after. So, no. So now we have n spins, and they're monitored through a network that consists of d layers, and so each rectangle here is maximally sorry, not maximally, using some random beam splitters, and they're organized in a brick pattern, and they consist of d layers. And so first of all, if we keep D fixed and we scale up N, then we see that clearly that we get some volume law both in system size and in subsystem size. And this is not so surprising because also here we know that these jump outcome probabilities are easy to sample. In particular, the permanents from this unitary, they are all band diagonal, so we can come up with a polynomial time algorithm to sample or to evaluate these probabilities. And then the other scenario is if we have now descaling with L, so it's proportional to the system size, and then we clearly see that there is a volume law scaling of the entanglement or the maximal entanglement entropy that you reach between spins as they decay. And that brings me to my conclusion and a few open questions. So first of all, I tried to illustrate that there is a correspondence between this monitoring induced and measurement induced phase transition, and that we can see a transition in entanglement entropy from critical scaling, so logarithmic scaling, to area law by changing the rates between two competing monitoring processes. And so still an open question is, because we now had a number conserving problem, but if we lose that, if we have not number conserving, can we also get the volume law scaling maybe? And then the other thing that I showed was that if you change this monitoring now of the same dissipative process, you can go from easy sampling of the quantum jumps if you would just do direct measurement. If you have like a fixed step interferometer, to a situation where the sampling of the jump click outcomes is hard, is classically hard, and this corresponds in particular with Boson sampling. And at the same time, we generate entanglement between our spins as we detect the clicks through the interferometer. And then last, and this is more the outlook, so how can we show correspondence between boson sampling or hardness of boson sampling and this measurement or monitoring induced phase transition? And so for this, we have to look into larger systems, and therefore we want to look into fermionic or fermion sampling or Gaussian boson sampling. And then we can come up with some networks that have a localization or a percolation transition for these unitary from the network. And we can also look at monitoring different quadratures, so in a homodyne measurements scheme. And then we can also look what if we take into account these decay times of the photon. So if we also keep track of the photon as it traverses the network, because then we have to take into account bath relaxation, and maybe we can somehow engineer non-Markovian processes this way or nonlinear decays or something. Yeah, that was it. Thank you.
So we have time for questions.
Mhm.
The plot that you're showing entanglement of a function of x, do you expect them to be symmetric?
Could you repeat the question?
Yeah, so the question is, so in this, the plot of entanglement entropy as a function of the number of clicks detected, isn't it expected to be symmetrical? And that is a very good question, because I've been wondering so too, and I think, but it's something that I have to, that we cannot check actually, because now we have to rely on MPS simulations or exact simulations. But I think if you go to larger system sizes, it can become symmetric, but for smaller system sizes, it's not symmetric, because these unitaries are now sampled from just the Haar measure, and it seems they're not symmetric, but I don't have a definite answer to that as to why it is like that. But it seems it gets more symmetric as you scale up system.
Maybe a very general, very evil question.
Mhm.
So I guess I'm teaching the AMO course, and we talk about open quantum systems. And so, the trajectories picture of evolution is sort of, I feel that it's the easiest picture to teach somebody that's not going to be actually doing it. But how physical do you think the jumps are? Like this, you've
No.
very carefully set it up so that there's a thing that you've defined that goes click
Yeah,
in
yeah.
each of these protocols. But we draw the same picture even if we don't put a detector there. This is more of an opinion question.
Yeah, that's almost like a philosophical question, I would say, because I mean, first of all, the whole point here is that you keep track of the clicks, and then you can, in this way, if you have this click sequence, you can reconstruct pure state trajectory at any time. However, if you do not keep track of the clicks, then you always end up in a mixed quant. Then you just have master equation evolution. So actually, you gain information by doing this unraveling and by keeping track of the clicks. And this tells you information, or this gives you information about the system, and therefore you get access to more information. Whereas if you just do master equation, you don't have this information, and then you just average overall possible outcomes from the clicks. That's the way I see it. Yeah. No.
Can I ask a question?
Yeah, sure. Yeah.
Okay, actually, my question is very much in the spirit of Alicia's question. When the quantum trajectory method was first developed by Dalibor and Carmichael and Zoller and people like that, the motivation, as I understood it at the time, was that for a system that had a large number of degrees of freedom, doing the master equation was just too cumbersome. You didn't have enough computer memory. And so this was an alternative. But at the same time, it offered a different picture of the way the quantum mechanics was going on. Now, you're not really worried about the difficulty of solving the master equation, if I've understood. In your case, it's all about having this different viewpoint of how to do quantum mechanics. And back then they would have said, well, we don't learn anything different. We're just enabled to do the calculation, and maybe we get some insights that are different. And I think they did. And I think we continue to get, sorry about my voice, we continue to get insights, but it sounds like you're actually learning something new this way. Could you expand a little bit on that?
Yeah, no, it's a good question. So initially it was introduced for, say, computational purposes, because if you have a master, say if you have a Hilbert space of dimension n, your master equation, so your density matrix has n square elements, so like you need a Hilbert space squared, or dimension of Hilbert space squared, to do integration of full master equation. Okay, it's not entirely true because you have some constraints. Anyway, but with these trajectories, if your system is large enough, you only need the dimension of the Hilbert space, because you have a pure quantum state at any time. And then you can run a few trajectories, or well, usually a number of, I don't know, depending on what you want to compute, and then you average over these trajectories. And this is more efficient than the master equation. However, in the, I don't know exactly what the original paper was, because it was roughly at the same time also the paper from Mulmer and Dalibor in Castan, where they really make the connection with the physical information that you can extract from your system by, or how it is associated exactly to this monitoring and extracting information from the system. Because now you keep track of all your jumps and you keep the whole record. And from these records, you can, in principle, reconstruct at any time a pure state of your quantum system. So there's no master equation that you need, or no mixed density matrix that you get just by keeping track of all the jump clicks. So in one way, I think, or it was presented as a computational advantage. And then on the other side, they also made a connection with the physical reality. If you have some dissipative system, and you can monitor the jump clicks. That is actually what corresponds to these trajectories.
Well, but I guess that as long as the jumps are something that you in a sense imagine in your computer, connecting that to physical reality is just a point of view. But,
yeah, okay.
But if you have real
of,
detectors, then it's different.
Exactly, but that's here the connection that I aim to draw. Like if you have, okay, for the purpose of simulations, it's exactly the same, and it's just numerically more efficient, at least if system sizes are large enough. However, there's also this correspondence, or at least belief. There is also this correspondence with physical reality if you keep track of all these jump clicks. Say if you do an experiment and you can really write down all the clicks you see, you can really, or at least, I don't know, it's a matter of perspective perhaps, but you can at any time reconstruct your pure quantum states again. In case you have, well, I don't know, a perfect efficiency and everything, of course. But,
yeah, if you have perfect detectors, so let's just assume that, and actually do the experiment instead of just run it on a computer, then well, you know what happened, and I guess, as you say, you can have a pure, you can tell what the pure state is between the measurements. If you'd made different measurements, you would have gotten a different set of pure states. It all would have led to the same master equation if you averaged over a bunch of things. I'm just trying to get my head around what do you learn that's new?
yeah, but it's something that we gave a lot of thought to. Like, also, what does it mean exactly changing the monitoring in particular? No, because you have the same, you keep the same master equation, so everything that you can directly measure is the same. However, the entanglement entropy of your trajectory states changes, but what does that mean exactly? Because it's not something that you can straightforwardly measure, because it's a stochastic state, and this one has some entanglement, but in order to measure entanglement, you would need a copy of that state. So you cannot easily measure it. So what does it mean? And it's a good question, and I must admit that I don't have a definite answer to that, and we've been thinking about it a lot.
Yeah.
Too.
Well, one of the things that just comes to mind is, what if you then used the information from these jumps to feed back to the quantum system?
Yeah, exactly. Yeah,
to do something entirely different.
yeah. And also, actually, now that I think of it, if you think of this Mandel example, so you can really do, say, a post-selection where you see one jump click in, say, the first detector, and then you always generate the same Bell state, and you can do a Bell measurement, and you can, I don't know, violate some classical inequality. Whereas if you do another monitoring, you can not do that. So that's really a difference, I would say.
Yeah. Thanks.
If you have a fancy enough setup in superconducting circuits, you can sort of clean the initial state of your qubits. Like, you know, in a master equation point of view, it's some mixed state with a probability of being in the excited state. But if you have the ability to check,
yeah, exactly, yeah.
And you start with a known pure state, it's just not always the same pure state from run to run. And if you can do this fast enough, you can just fix it.
Yeah.
And so, like, I think there's a very, very useful picture for an experimentalist between sort of a mixed state and just an unknown pure state that's not always the same. You know, if you imagine that somebody feed you spin up sometimes and spin down sometimes, if you knew which one you had, you could fix it.
Yeah, exactly. Yeah, so you can.
But from a master equation point of view, this is just some random mixed state.
Exactly. Yeah. So that's.
If you get the click, then you have the information to fix it.
Yeah.
That's what's going on.
Yeah, and you can also do some feedback, as Bill said, where you then, if you want the spin to be up, you can just excite it again or something if you know that it is decayed. Yeah. So that's yeah. So you gain more information about the system. And if you just look at anything that you measure from the system, it's pretty much the same. Whether you do